Thank you very much for the invitation. I'm sorry I couldn't be there. I wish I could be there with you in person in Norway. It's a big, busy holiday weekend here in the States, and but I couldn't pass up the opportunity at 8 a.m. on Sunday morning to tell you about unexpected applications of fully homomorphic encryption. I'll assume my audio is okay unless you say otherwise.
Perfect.
Okay, let's dive in. So as we probably all know, fully homomorphic encryption was proposed by Revest, Edelman, and Dertouzos in 1978. And they said, let's conceive of an object or a cryptographic tool that would allow us to do this. We have some message data, we encrypt it under a public key to get a ciphertext. And throughout the talk, I'll use a hat over some information or some data to denote that the data is now concealed somehow in a ciphertext, for example. So we get the ciphertext, which conceals the message data, and then we can apply some evaluation algorithm to together with a function f and obtain an encryption of the function applied to the message data. And after we've done that evaluation process, we can decrypt using a secret key, and we get out not just not the message M, but rather the function applied to the message M. And this was a cryptographic holy grail that was proposed, more than 3 decades ago, 3.5 decades ago, and first solved by Gentry in 2009, followed by a long series of works proposing different varieties and variations on the initial theme of Gentry's work. So this cryptographic holy grail, as you might expect from a holy grail, has countless applications in cryptography, but some of these are more surprising than others, in my opinion. And so what I'd like to tell you about in this talk are some of the unexpected uses of fully homomorphic encryption. So just to kind of get some things out of the way, these are some applications that I would consider less surprising. Not that there's anything wrong with them. They're great work and really non-trivial problems to solve. But if someone told you, I've solved this problem and I used fully homomorphic encryption to do it, you might say, yeah, that makes sense. That doesn't totally surprise me. So that includes the kind of canonical prototypical application like private cloud computation, where you upload your encrypted data to a cloud and the cloud does computation on it. Low communication multi-party computation would be another example that's long been viewed just as sort of encrypted computation among many different parties. Code obfuscation, similarly, you're kind of encrypting some code and running the code in a way that you can't understand, make any sense of. Quantum FHE, of course, the word FHE is right in there, so not too surprising that that would use FHE schemes. And so on and so forth. There are many applications. So today, instead, we'll talk about some of the more unexpected applications, at least more surprising to me. If you had told me that FHE would be useful for these purposes before they were introduced, I would say, oh, that's kind of interesting. That's surprising. The first of these is instantiating random oracles for particular purposes, including specifically non-interactive zero-knowledge proofs. And the second of these is something called attribute-based encryption. And I hope with the time that we have, I'll be able to give you a flavor, if not some details, on how each of these works and how FHE comes to provide the kind of key tool to achieve both of these results. And the common theme between the two of them and many follow-up works is that there's really some non-obvious computation on hidden data. So that's what fully homomorphic encryption allows you to do. It allows you to compute on hidden data, but it's not clear in these constructions or even in the concept of non-interactive zero-knowledge or attribute-based encryption. It's not totally obvious in advance, like how does encrypting on hidden data or computing on hidden data really help you for that purpose? And a second common theme is that neither of these applications involves any decryption of the computed hidden data whatsoever. So there's really no final decryption. There's something else going on under the covers that makes this hidden computation useful for the purposes of these applications. So those are the two themes. I'll hope to show you, a significant amount of the ideas behind these two different applications. So let's jump in to the first one. We're talking about instantiating random oracles with concrete functions for the purposes of getting non-interactive zero knowledge. So let's review a little bit about zero knowledge and zero knowledge for the class NP of languages that have efficient proofs. So that it was first shown by Goldreich, Mercalli, and Vigerson in 1986 that if one-way functions exist, then every NP language, like 3 satisfiability or Hamiltonian paths or all the rest, has a zero knowledge proof or an argument in the case of Nguyen, Ong, and Vadan in 2006. So there are many, many applications of zero knowledge, of course. You can use it to identify yourself, to prove that you know a secret without revealing anything about that secret. It's used all over the place in multi-party computation and on and on and on. So to give it a flavor of how this result is achieved, it's sufficient to give a zero knowledge protocol for the NP complete Hamiltonian cycle problem, because Hamiltonian cycle is NP complete. Any NP language can be reduced to it. And so all you need to do is give a proof that a particular graph contains a Hamiltonian cycle. And just to recall, that's a cycle that goes, that starts at one node, goes through every node exactly once using edges, and then returns to the original node of the graph. And it goes through every single node of the graph. So the way this protocol proceeds in an interactive fashion is that the prover has the graph and knows a cycle in the graph, and the verifier just has the graph. And the prover wants to convince the verifier that indeed there is a Hamiltonian cycle in this graph. So the first thing the prover does is it randomly permutes the graph G to get a new graph H using a permutation row. And then it commits to this new graph. So concretely, it will commit to all the edges or non-edges in the adjacency matrix of the graph. So this is a bit indicating whether there's an edge between I and J, and it gets a commitment Cij. And then it also will commit to the permutation row that it used. And then at this point, the verifier will challenge the prover with one random bit. And depending on the value of the bit, the prover will do one of two things. If the challenge is 0, then the prover will simply open up all these commitments for that it sent in the original message, and check that indeed the verifier will check that indeed the prover committed to a permutation of the graph G. Okay, so it just kind of opens up all the commitments that it sent in the first message. In the case that B is 1, something a little more interesting happens. The prover will open up all of these edges of the permuted graph that lie in the cycle that it knows. So these IJs are in the cycle. Of course, the graph has been permuted, so the cycle has been permuted correspondingly. And so the prover only opens up the sequence of edges through H, through the permuted graph H that yield a Hamiltonian cycle. And the verifier can then check that the cycle, that these edges really do form a cycle. So why does this prove that the graph has a cycle? Well, if the prover is able to answer, is prepared to answer both of these challenges, then indeed this information in the first message must be a commitment to a permutation of G, and that permutation of G contains a cycle. So if a permuted G contains a cycle, then G itself must contain a cycle. Why is it zero knowledge? Well, the verifier gets only one of two things. It either gets just a permutation of the graph, which is not telling it any information it didn't know. You know, it could have created a permutation of the graph itself, or it's getting just a bunch of openings of commitments that are just all ones, just showing that there's an edge here, there's an edge here, there's an edge here, and they form a cycle. But it doesn't learn anything about how that cycle corresponds to the original graph G due to the hidden permutation. So this is sort of, very nice protocol for proving Hamiltonicity. Now, interaction of this kind between a prover and verifier is not always possible. And so Blum et al. In 1988 said, well, what if we had just the ability for the prover to send a proof directly to the verifier, and it would accept or reject, and this proof not only was convincing, but also was zero knowledge. Unfortunately, in the plain model, just as the picture I've shown here, the only things you can prove in this way are trivial languages in BPP. So languages that the verifier can verify itself, the prover provides no help in this case. However, if we change the model a little bit and introduce the idea of a common random string or reference string that's up in the sky that both parties can look at, then we can actually prove any NP statement in non-interactive zero knowledge under a variety of different cryptographic assumptions. So there's been a long history of building non-interactive zero knowledge proof systems under various kinds of assumptions, and also applications of NIZK. So signatures, chosen ciphertext secure encryption, cryptocurrencies, they're a huge thing right now, in addition to concision, which I won't talk about today. But it was open for quite a long time, starting around 2008, when we first explicitly posed the question of, can you build NIZKs using some kind of post-quantum foundation, in particular lattices, or the famous LWE lattice assumption, and so forth. And we were able to build applications like signatures and secure encryption using other techniques, using lattices, but still the NIZK itself remained out of reach. So finally, a few years ago, the culmination of a series of works, we were able to show that every NP language does have a non-interactive zero knowledge proof under standard LWE type lattice assumptions. So we'll give a flavor of how this is achieved, and as I already alluded to, it's actually achieved using fully homomorphic encryption or fully homomorphic computation type techniques that we'll go over. In addition, the result is achieved using what's known as the Fiat-Shamir transformation, or the Fiat-Shamir heuristic, which was proposed back in 1986. So this is a way of actually removing interaction from a protocol, a public coin protocol, using hashing. So the idea is, if you have an interactive protocol here on the left, where the prover sends some message A, the verifier responds with some challenge beta, and then the prover replies with the response gamma, you can squash this down, flatten it into a non-interactive protocol. And the transformation says, let's work in the common random string model or common reference string model, where the common string specifies some hash function H. And then instead of being non-interactive, when the prover wants to prove something, it will prepare its message alpha as before. And then instead of waiting for the verifier to reply with a challenge, the prover will compute the challenge beta just by hashing the message alpha. Actually, it would usually hash the statement itself too, but let's leave that out for now. So it will hash its initial message alpha, and then it will say proceed as if the verifier had sent beta as the challenge, and prepare the response gamma and send all of that over to the verifier. Okay, so that's the transformation. And it's pretty easy to show that if you transform a protocol in this way, that completeness is preserved. That is, the prover can still execute the protocol and successfully convince the verifier. That's straightforward. And even zero knowledge for an honest verifier is also easy to preserve. You just kind of do some programming of the hash function at one point using a simple, kind of XOR or something like that. And you can get zero knowledge quite easily. The real challenge about the Fiat-Shamir transformation is soundness. That is this transformed protocol sound, or is it possible for a cheating prover to convince the verifier of a false statement? Okay, so in the left-hand side, we assume that this protocol is sound. The verifier will catch a cheating prover trying to prove something that's false. But the question is, over here, could a cheating prover prepare some kind of special alpha so that beta works out and everything fools the verifier, right? So are there any alphas and gammas where the challenge beta that's computed using the hash function is able to fool the verifier? And a priori, it's not clear how to answer this question. The prover may look at the hash function and say, oh, I can do some kind of reverse engineering or something, and I can cook up an alpha that gives me just the beta challenge that allows me to finish the proof. So that's really the core question here. Can a cheating prover find these appropriate values, alpha and gamma, that will fool the verifier. Okay, so there's been a series of works for many years, but especially recently in the past 5 years or so, addressing the question of how to instantiate Fiat-Shamir in a sound fashion, where a cheating prover can't succeed. And what was noticed is that one way to achieve this is to use what's called a correlation intractable hash function or hash family. And basically what a correlation intractable hash family is, it says if you choose a random hash function from the family and put it up in the common string, then it should be hard or even impossible to find an alpha such that alpha together with its hash value is in some specified relation. In this case, the relation that we're interested in is alpha and the pairs alpha and beta, right? Where beta is sort of the challenge, right? So a string alpha, a beta, such that there exists a third response, right? A response gamma that will make the verifier accept. Okay, so our relation is we'd like it to be hard to find an alpha such that beta, which is the hash value, allows the prover to complete the fooling of the verifier. Okay, so more specifically, a theorem that was shown by Holmgren and Lombardi and then extended by Canetti et al. Is that we can get all NP languages in non-interactive zero knowledge, assuming we have a correlation intractable hash family that is intractable for all polynomial size but bounded size circuits. Okay, so the specific relation that we're interested in is R sub C, where R sub C consists of all the pairs alpha and C alpha, where C is an arbitrary circuit of bounded polynomial size. Okay, so this is the theorem that they showed, and why is this sufficient to instantiate Fiat-Shamir soundly? Well, the idea is if we consider that Hamiltonian cycle protocol from a couple of slides ago, each alpha is a commitment to a permuted graph, right? And in fact, we'll repeat this in parallel m times to bring the soundness error down a lot. So we're running this protocol a bunch of times in parallel. Each potential alpha is supposed to be a permutation of the original graph, independent permutations, m of them. Well, each of these permutations has at most one bit which will allow V to be fooled, right? So if the graph really doesn't have a Hamiltonian cycle, then the prover, the cheating prover, is forced to either commit to that graph, okay? It can commit to that graph in an honest way, basically, but then it won't be able to provide a cycle in that permuted graph because the cycle doesn't exist. So it will fool the verifier if the verifier happens to say, hey, open up the commitment, right? And then the prover will be able to complete the proof. Or the prover can commit to some different graph that does have a cycle, and it will be able to respond to the challenge of 1, but it won't be able to respond to the challenge of 0. It won't be able to open up the commitment and show that that's a commitment of the original graph. So no matter what the prover does for each original message alpha, there's at most one string of bits or string of challenges that will allow the prover to complete the proof and fool the verifier. If any other challenge is produced, the prover is stuck and will not be able to complete the proof. So why is this useful for us? Well, this fooling challenge, beta, is actually efficiently computable if you have some kind of trapdoor that allows you to open up the commitments to these original graphs. Okay, so for opening the original commitments, if you have a secret key that lets you look inside those commitments, then you can efficiently compute what is the fooling challenge beta for all of them. All right, and what this theorem says, or the proof of this theorem says, is that, well, because this is efficiently computable, let's consider the circuit C that actually does this computing of the fooling challenge, right? So there's a message that the prover sends over. There's a secret key that we can bake into a circuit C. that circuit actually will look at alpha and compute the fooling challenge, 10110, whatever it is, the one single bit string that fools the verifier, that would fool the verifier, and it can compute that. And correlation intractability says, well, it's impossible or infeasible to find an A whose hash value beta is exactly that fooling challenge. So the prover has no choice but to, whatever it does, it cannot come up with an alpha whose hash is the fooling challenge that it needs to get back that would allow it to prove, finish the proof. Okay, so this is the flavor of the theorem. And it says, basically it reduces the question of NISIC for NP to the question of building a correlation intractable hash function for all bounded circuits C. Okay, so let's actually do that construction. We can actually build a correlation intractable hash family for all bounded polynomial circuits C, and it uses homomorphic encryption, or actually homomorphic commitments, as we'll see. So I'll skip over this, but I'll just mention that this can be done in two ways. It can be done in a way where it's hard to find or infeasible to find an alpha that hashes to the C of alpha value, the fooling challenge, or it can be done in a statistical way where there simply does not exist such an alpha. And this gives you an actual proof system that's computationally zero knowledge. Okay, so let's get to the homomorphic encryption part. The key tool that we'll build here, or that we'll use here, is not fully homomorphic encryption, actually. It's a kind of stripped down version of it, which is fully homomorphic commitments. So this is based on the FHE scheme of Gentry, Sahai, and Waters, and then stripped down to a commitment scheme by Gorbanov, Vaikuntanathan, and Wee in 2015. Wicks, I'm sorry, not Wicks. So the idea is a stripped down version of what I showed before. The message goes into the commitment. There's also some randomness that goes into the commitment algorithm, and you get out a commitment to M, which has this M hat, right? And then you can do homomorphic evaluation, and you'll get a commitment of F of M. So very simple, but there's no decryption here necessarily. What there is an additional feature, which is that if you also provide the randomness, one thing about this is that the commitment is statistically hiding. So in fact, this M hat may not uniquely define M. There may be, for every possible message, there may be some randomness that will open this commitment as some other M prime. So that's not possible in fully homomorphic encryption, but it is possible with commitments. Okay, so now there's this additional feature that we'll call randomness homomorphism. If you provide the randomness that was used to produce M hat, you provide this randomness to the homomorphic evaluation, it will also spit out valid randomness for the resulting commitment here. Okay, so you can do this evaluation without the randomness and just do it on the public, hidden, the public commitments. But if you also provide the secret randomness as input, you will get the corresponding secret randomness as output here. And this is really a critical feature that we'll use throughout the entire rest of the talk. So let's see how this helps us to build a correlation intractable hash function. So our goal, again, is we'd like to have a correlation intractable hash function for circuits of size up to S. And we'll use fully homomorphic commitments to do this. So the idea is follows. Well, the hash key, the description of the function, is going to be a commitment, a fully homomorphic commitment, hat D, to some just dummy circuit. It's a circuit that doesn't matter what it does. It always outputs 0 or something like that. Just any circuit that has the same domain and range as our circuit C. And to evaluate this hash function on an input alpha, we'll do the following. We'll take the description of the function d hat, and we will do homomorphic evaluation on it to compute the commitment to d of alpha. Right? So we're applying this encrypted circuit to the input alpha, and we get out an encrypted d of alpha. The second thing we'll do is a step, kind of a compressing step, or I call it inertifying step. And it's basically just squashing down the commitment and applying a special linear function to the underlying data. So we're going to get out some commitment C alpha here, which is a commitment to G of D of alpha. And the flat bar on top indicates that this is an inert commitment. It means you can't really do any further homomorphic operations on it, but you've squashed it down to be a vector of a certain size. So it's a much smaller commitment than the one with the hats on them. All right, and then the final thing is to just output the binary representation of this inert commitment. So I'll denote that by G minus of the commitment, and this is simply the binary vector Y, such that G of Y is the inert commitment here. And this G is the same linear function here. So you can think of G as G minus as the bit representation of a vector in ZQN, and you can think of G as reversing that and putting the bit vector back into ZQN. Okay, so that is the hash function. It's just homomorphic evaluation on the input, inertifying, and then outputting the bit string. And the key point to this that's going to make it work is that this inert commitment C alpha, it's a vector in ZQN, but it also commits to a value in ZQN, right? Because note that this G function outputs a value in ZQN. So the value under the flat bar here is itself a message or is data in ZQN. So we have a commitment that commits to a value that's just as large as the commitment itself, or it's from the same domain as the commitment itself. And that is going to let us compare the commitment to the underlying value that it commits to, and not just reason about the committed value alone. And that's going to be the key point in the security proof. So let's take a quick look at how this security proof will proceed, just an overview of it. So again, the hash key is a commitment to a dummy circuit, and to evaluate on alpha, we homomorphically apply D on alpha. We apply this function G homomorphically again to get an inert commitment, and then we output the bit representation of it. So what we'd like to show is that it's hard to find an alpha input such that H of alpha equals C of alpha. That's the definition of correlation intractability. So let's suppose, for the purpose of contradiction, that an adversary, after being given this hash key D hat, is able to find an alpha that hashes to C of alpha for this circuit C. Okay, and we'll build, we'll show that this is kind of impossible by reduction. So the first thing to observe is that by the security of the commitment scheme, either the statistical or computational security of the commitment scheme, the same is going to hold if we replace the hash key D hat with C hat. So this is the normal way that we evaluate things. But let's imagine that we swap out the contents of the original commitment with a commitment to our circuit C here. All right. So in red, we have the circuit C, which is a commitment to our circuit under some randomness RC. Okay, and so what we have now is that the adversary is able to find an alpha such that this new evaluation, G minus of the inert commitment G of C of alpha equals C of alpha. Okay, and now we kind of are in good shape. What we can do is take this equation here and apply G to both sides. So we just send the bit strings to ZQN, and G inverse, G and G minus cancel out, and we're left with this inert commitment to G of C of alpha equals G of C of alpha. So that's what you get by applying G to the right-hand side here. Right? And both sides of this equality are in are vectors mod Q. So basically, the inert commitment C alpha here itself equals the value that it commits to, right? That's what this equation is saying. So the commitment to G of C of alpha is G of C of alpha. And two facts which allow us to complete the proof are the following. First is that since we've set up the hash key by committing to C using randomness that we know, this is in a security proof, we know the coins for the original commitment C hat here. We can homomorphically compute the underlying coins for C alpha, right? So all this homomorphic computation on C hat that we performed, we can track through what happens to the coins. And if you remember, our homomorphic commitment allows us to also know the coins for the underlying commitment C alpha here, for the final commitment C alpha here. And then the second fact, which allows us to complete the proof, is that generating a commitment that equals the value it commits to turns out to directly solve the SIS lattice problem, right? Which is assumed to be infeasible here. So the point is basically that finding an alpha that hashes to C of alpha allows us to homomorphically operate on the original random coins, get some kind of derived random coins R alpha for a commitment that equals its underlying message. And this is actually infeasible to do using SIS. So this proves that an adversary cannot achieve its goal of finding an input that hashes to C of alpha. Okay, so just some kind of high-level observations about this and what it has to do with homomorphic encryption. So the homomorphic computation here has been done on the common random string. The common random string specified the hash function. It was a commitment to a dummy value. It was a commitment to either a dummy circuit, but inside the security proof, we swapped it out to be a commitment basically to a trapdoor that lets us compute the fooling challenge, right? So the circuit we're interested in having correlation and tractability for is the circuit that computes the fooling challenge beta from the commitments to all these graphs alpha. So in fact, there's another interesting aspect of this, which is this is another example showing the power of homomorphic decryption. So this circuit CSK is actually decrypting these graphs and looking at them and finding which, does the graph have a cycle or not, and so forth. So this is actually another kind of example of bootstrapping in disguise, if you know what FHE bootstrapping is. This circuit is doing homomorphic decryption along with other operations. A third thing to notice is that the commitments are never opened in the construction. They're never opened at all. The commitment is operated on homomorphically, and in the end, you just spit out the binary representation of some homomorphic commitment, but you never decrypt it, you never open it. But the key point is that being able to break correlation and tractability implies being able to construct an infeasible commitment because of the randomness homomorphism. So it's not that we really care too much about the computation on the encrypted data, but we also care just as much about the homomorphism on the underlying randomness in the commitment. So I think that's kind of all pretty unexpected in at least in pre-sight. In hindsight, it all comes together quite nicely. Okay, so that was correlation and tractable hashing. I'll give a more brief overview of attribute-based encryption and how FHE plays into that. So attribute-based encryption was introduced by Goyal et al. In 2006, and it's a kind of generalization of identity-based encryption. The idea is that secret keys will have policies associated with them, policies F, and ciphertexts will have what are called attributes A associated with them. And a secret key can decrypt a ciphertext if and only if the policy is satisfied by the attribute. So say f of A equals true, meaning authorized. Okay. So the exact syntax of this is 4 algorithms. I won't go through them in too much detail, but basically the important one is that there's a master secret key for which you can derive secret keys for specific policies. And using such a secret key, you can decrypt a ciphertext if and only if the policy is satisfied by the attributes. Otherwise, you can't decrypt it. You learn nothing. And the security requirement is basically that for whatever the targeted attributes are, a ciphertext hides its message, as long as you are only given secret keys for policies that are not satisfied by the attributes. Okay, so you can have secret keys for all the policies you want, but if they don't, if none of those policies are satisfied by the attributes in the ciphertext, you learn nothing about what's in the ciphertext. So the tool that has been used to build this attribute-based encryption basically for any policy, like arbitrarily complex policies, is an extension of these homomorphic commitments, but augmented with encryption. So the picture up top in blue here is exactly the same as before. You can commit, you can use that commitment and perform some evaluation on it to get a commitment to F of M, the randomness. If you give it to eval, you get out the corresponding randomness from eval. But now we have an additional encryption aspect to this. You can take a message and encrypt it under a specific commitment M hat. Okay, and that will produce a ciphertext. And then you can operate homomorphically on that ciphertext. You can run what I'll call eval CT with a function f, and you'll get out some derived ciphertext. And you can decrypt that ciphertext if you have the randomness of the corresponding derived commitment. Okay. What comes out is just the original message. So no homomorphism is being operated upon on the message itself. What's happening is that the keys are kind of being operated on homomorphically. So this is the public key that goes into encryption. It itself is a commitment. And then as you do eval, the notion of what is the corresponding public and secret key is changing homomorphically. So now this is the corresponding public key. This is the secret key for the ciphertext. And if you provide that secret key to DEC, you will get out the message here. Okay, so this is what I've just said. The commitments act as public keys. The homomorphism kind of tracks what's happening to the commitment and the randomness, but it doesn't actually operate on the message. And if you have the commitment randomness, you can decrypt the corresponding ciphertext. And we can prove that this is secure, assuming LWE. So here is how we can use this augmented scheme to construct attribute-based encryption. This was shown by Bonnet and many others in 2014. So the setup is actually kind of pretty similar conceptually to what we had before. The public parameters are just a dummy commitment. They're a commitment to all zeros, for example, under some randomness R, and the secret key is that randomness R. If you want to extract a key for a specific policy F, what you will do is first homomorphically evaluate F on this dummy commitment. So you get a commitment to F of 0, right? And we can set up this dummy value so that F of 0 is always accepting, is always true, just with some simple encoding tricks. And what's important is that the corresponding randomness RF is available to you. So if you knew the master secret key, then you know the underlying randomness for this dummy derived commitment here. And that secret key is essentially the secret key for policy F. You have to do some re-randomization, which I will skip, but that's the basic idea. So you can give out this secret key for any policy F you like by just doing the homomorphic evaluation and tracking what happens with the randomness of the commitment. In order to encrypt, we're going to use of course, the augmented encryption functionality here. To encrypt to specific attributes A, what we'll do is change the public parameters to kind of shift them by A. So we'll get a commitment to negative A by just subtracting a kind of trivial commitment to A here with 0 randomness. And then we will encrypt relative to this negative A hat commitment, right? So remember this commitment can act as a public key, and we will encrypt the message relative to this commitment as the public key. And then the magic happens in decryption. So in decryption, we have this ciphertext CA, and we're going to run the kind of corresponding evaluation on the ciphertext, the homomorphic evaluation on the ciphertext with our function f. And the magic of the eval-CT protocol, or algorithm rather, is that we get out in the end an encryption of M with respect to, well, still COM of F0 with this randomness, but it's been similarly shifted by a commitment to F of A with still with 0 randomness. So this shifting that we do up here kind of passes through eval-CT cleanly, and now we have an encryption of M relative to this derived commitment, but similarly shifted by F of A. And so we can complete the decryption. We can actually successfully decrypt as long as our secret key that we were given out above is a valid valid randomness for this first part of the commitment. And that's equivalent to saying that if this F of A is 0. So we can, this term here will vanish exactly when F of A is 0. And that's what we define as to be our authorization rule. So basically, if the policy is satisfied by the attributes, this F of A is 0, and this whole thing goes away, it vanishes. And so we have a ciphertext relative to this piece, but our secret key is exactly the randomness RF right here, and so we can decrypt. If our policy is not satisfied by the attributes, this is something non-zero, and it messes up the attempt to decrypt using the randomness. Okay, so that is just a flavor of what's going on. I'll skip the overview of the security proof, but it's very similar to what we did before. I'll just say that we substitute the dummy public parameters, right? These public parameters are of a dummy value. We're going to substitute them for the targeted attributes, and it makes it so that the simulator will know a secret key exactly when the only for policies that are satisfied by the targeted attributes. Okay, so some closing observations just to reinforce the theme. Here, our homomorphic computation is not done on what we consider to be the message data. The message data has never changed in attribute-based encryption, but the computation is instead done on the public parameters, which are a commitment. And that fully homomorphic commitment, again, it hides either a dummy value in the real reality, but inside the security proof, it hides the attacked or targeted attributes A star. And what this allows us to do in the proof is to kind of puncture the public parameters so that the simulator only knows secret keys for policies that are satisfied by the attributes. So the simulator can give away all the secret keys it wants for policies that won't decrypt the challenge ciphertext, but that's all it can give out. So actually, I feel like I have it somewhat backwards here. Only knows secret keys exactly when F is authorized. I think it should be not equal to top here. Sorry about that. Okay, so this lets the simulator give out secret keys for policies that are not able to decrypt the challenge ciphertext, and that's kind of the core of the whole proof idea. Okay, so just to wrap up, I'll mention that there are many further variations on this theme, many works, too many to name, but a couple notable ones are using this attribute-based encryption. Goldwasser et al. Showed how to get what are called reusable garbled circuits, and that builds on top of the ABE scheme. Let's see, Gorbanov, Vaikunthanathan, and we showed how to get predicate encryption where the attributes are actually hidden from also building on this ABE. A totally different line of work gets what are called privately constrained pseudorandom functions. And that's another case of using homomorphic encryption inside the computation of a pseudorandom function, which is a symmetric key primitive. So that's another example. sort of surprising of homomorphic encryption. And then very recently with our students, we gave some succinct functional commitments also using these kinds of techniques. So the sky, I think, is the limit. Whatever your next great idea is, think about whether these kinds of ideas are applicable and or would help you solve your problem. And with that, I'll thank you for your attention and take any questions you have.